In this video, we're going to look at deriving a formula to find the length of a curve. So when we say curve, we basically mean we could have some function. So here we've got a function f of x, and we want to find the length of the curve from A to B. So we would have some scale here, right? This would be 1, 2, 3, or whatever. So whatever this 1 is, say it's in feet, that would be a distance in feet, or whatever you're measuring it in. And if we curved around this curve with that particular length, and we followed the curve where that length could be wrapped around this curve, how many feet would it be? That's what we're trying to figure out. So as like a lot of things in calculus, we're going to approximate this by using some method of finding length that we already know. And so in this case, if we want to find the length from A to B along the curve of f of x, we're going to create a partition like we've done many times, and then we are going to approximate this length in the first interval by just finding the direct straight line length between this point at x sub 0 and this point at x sub 1. And we could see it's not going to be a great approximation. It's going to be a little bit less than the actual arc length. But this next interval, we can approximate this distance here. It's going to be pretty darn close to the actual arc length, as you can see, because there's not a lot of gaps there. All right. So if we sum up these little orange segments, that's going to give us a great approximation to the curve, the length of the curve. So now, how do we find these orange lengths? Well, we're going to use the distance formula, right? So let's just remember the distance formula. Let's say I wanted to find this arc length right here. So the distance formula would be the square root of the x value minus the x value squared plus the y value, which is f of x sub 0, minus the other y value, which is f of x sub 1 quantity squared. It's basically the Pythagorean theorem is what it is. So another way we could think about what x sub 0 minus x sub 1 is in our partition. What is that in our partition? You remember? That is delta x, right? That distance is delta x. We're going to assume we have a partition of equal intervals here, and these are all delta x. Now, this distance right here, let me make it a little different color. Let's say this is red. This distance right here, that's this y minus y part. That's going to vary depending on the interval, right? Let's draw another interval here. So if I look at, I don't know, let's do this third interval. All right. If I look at this, finding this distance of this orange segment, that red change in y is different than this red change in y, right? Because depending on what's happening with the function. All right, and if I go to this next interval, here's the change in x, and here's the change in y, which is a little bit more than this change in y. So the change in y, the delta y, is going to depend on the interval. So we're going to say delta yk. Now the change in x for each interval is going to be the same. It's going to be delta x because of how we're creating our partition. All right, so of course that we know we can get a better and better approximation if we increase the number of intervals that we have. And here we have a picture of a very generic partition where we're starting off at x sub 0, x sub 1, x sub 2, dot, dot, dot. I don't know how many intervals I have. And I have some generic interval here in the middle, x sub k minus 1, x sub k, all the way up to x sub n. So what we want to do now is we want to look at some generic interval here, right in here. The width is delta x, and we want to pull out this little arc length and this straight line length and create and just blow up that picture and take a look at that triangle. All right, so I'm going to draw a picture of that on the next slide. Okay, so let's say we have some curve f of x here, and this is part of our partition. So let's say that this point right here is at x sub k minus 1, f of x sub k minus 1. And this point up here is at, here, let me move my f of x somewhere else. F of or x sub k, f of x sub k. And this is my f of x function here. And let's just call this distance right here d sub k that we're adding up. So remember, this distance down here is delta x. It's going to be delta x no matter what interval we're in. That's always going to be delta x because of the partition. But the height here, the change in y, is going to depend on the interval, so I'm going to call that delta y sub k. All right, so using our distance formula, we know that the distance there in the kth interval is going to be delta x squared plus delta y sub k squared. Now, a little bit of a thing here. Delta y could come out to be negative if the function was decreasing. So you might see some textbooks put this in an absolute value to make it a positive, but we're going to square it, so it's going to come out to be positive anyway. All right, so using our awesome calculus skills, we know that the length of the curve between A and B is going to be approximately the sum from k equals 1 to n, depending on how many intervals we have, of the square root. This is one little d sub k, right? This will give you 1 d sub k. I'm not going to write those absolute values. That's going to turn out to be a positive because we're going to square it. Okay? All right. So far, so good. Now, what do we want to do, calculus students? To find the actual length, what do we want to do? That's right. We want to take the limit as n approaches infinity of this summation. K equals 1 to n square root of this guy. All right. Now, many of you know this limit's going to turn into an integral, all right? But we have this delta x inside. That's going to become our dx when we do our integral. And we really want this all in terms of x. We don't want x's and y's in there. So we've got a little work to do with this, this business here. We've got a little work to do with this business before we actually change it to an integral. So that's what we're going to do next. So what I want to do is I really just want to focus on this bit right here. And we'll come back to the whole thing, the whole sum and the limit and all that stuff. But I want to pull that off to the side, and we're going to mess with this a little bit, okay? And then we'll put it back into our limit. So let's look at this business right here. All right, we're going to do something that may not seem intuitive at first, but what we're going to do, hopefully you'll see why, is we're going to pull out a delta x squared. Now, I want to be clear, this is not delta x squared, it's delta x, that distance, delta x, right? This distance, delta x squared. All right, so we're going to pull out a delta x squared from this thing. And what's that going to leave? Well, if I factor it out of delta x squared, that's just going to give me 1. Now, what would I write here? What would I have to write here so that delta x squared multiplied by whatever I write here will end up giving me delta y sub k squared? That might be a little tricky for some people. Let's think about that. It's going to have to be a fraction, and it's going to have to cancel out the delta x squareds. So I'm going to put a delta x quantity squared down there, and then this is going to be a delta y sub k squared right there. All right, so notice if I multiplied this delta x squared back into here, I should end up with what we started with. Now, why am I doing that? That looks like it's getting worse. Well, this is where the mean value theorem comes in. So let's remember the mean value theorem, which, let me pull that up. All right, that says when you're looking at some interval, there's some point inside that interval where the slope of the tangent line is equal to the slope of the secant line. All right, so let's go back to our picture and take a look at what that means there. So here we have our interval, our generic interval, and here we have the secant line. This distance dk, this line here, is the secant line between these 2 points. Now, what is the slope of that secant line? How would I find it? Well, it would be delta y sub k over delta x. Let's just write this on this slide while we're here. So the slope of the secant line is delta y sub k over delta x. Now the mean value theorem says that then if we look at this interval, all right, between, this is x sub k minus 1, x sub k, there's some value inside this interval. Oh, I don't know, let's call it x sub k star. All right, there's some value in this interval where the slope of the tangent line at that point would be equal to the slope of the secant line. So the slope of the tangent line at that point would look like that. We're going to call that point, guaranteed by the mean value theorem, x sub k star. So there's some x sub k star inside the interval, x sub k minus 1, x sub k, where the derivative at that point is equal to the slope of the secant line, which is why, okay, remember this, look at this, look at that, why we do this. Okay, so what we got from the other screen, we had there's some x sub k star in the interval that is equal to the change in y over the change in x on that interval. All right, so f, the derivative at x sub k star quantity squared would equal, what would it equal? Y delta y sub k squared over delta x squared, which is exactly what we have in our formula. So we're going to make that substitution. And then the other thing we're going to do on this next step is since this is multiplied here, we can take the square root of this delta x and bring it outside. And I'll probably put it at the end, but we'll put it here for now. All right, so we'll bring that delta x out of the square root. And what do I have left? 1 plus, and what's all that light blue stuff? Well, it's equal to that. F prime of x sub k star squared. Now, one thing to just keep in mind when we take the square root, when we do this part right here and we take the square root of delta x squared, technically it would be the absolute value of delta x, but we know that delta x is positive because it represents this distance. So when we take the square root of a squared, it's not always that number. Right? If I take the square root of -3 squared, it's not -3. It only works if it's positive. So just a little thing to remember there. All right, hey, we're almost done. It's pretty exciting. Let's go back to our limit, I think, and let's plug in what we've got. So all this stuff we did right here, all this stuff, we can plug in for all this stuff, right? That's what we manipulated. So let's see what we've got. That's what we were messing with. What do we got now? We got L is equal to, I want a little darker blue there. How about that one? The limit as n approaches infinity of the sum from k equals 1 to n. I'm going to move the delta x to the end of the square root of 1 plus f prime x sub k star squared delta x. All right, now we're ready to write this as an integral. So remember, when you go from a sum to an integral, your x sub k stars will turn into x's, your delta x will turn into dx, and your limit as n approaches infinity of your sum turns into your integral from a to b, and where your delta x is the b minus a over n, right? That's how you get your b and your a. So we can rewrite this as the integral. Let me write it over here. We have a little more space. So this is equal to the integral from a to b of the square root of 1 plus f prime of x quantity squared dx. Beautiful. There it is. That is the formula to find arc length. So in a future video, we will look at some examples, but this formula will give you the length between x equals a and x equals b for a continuous differentiable function.